So in the span of just 9 months, artificial intelligence went from playing tabletop detective games like a totally distracted teenager to basically outsmarting some of the brightest computer science students in London.
Yeah, it's a massive leap. I mean, we're talking about jumping from the bottom quartile of human performance straight into the top 5%.
Right, which researchers are classifying as, expert master detective levels of reasoning.
Yeah.
But here is the paradox that makes this entirely fascinating.
hmm
That same master detective AI, which can make these brilliant leaps from a single microscopic clue, will completely lose the plot if the story it's reading stretches past just a few pages.
It's such a weird contradiction, isn't it?
It really is. So today you are sitting right here at the table with us as we unpack a stack of groundbreaking research. We've got papers on AI reasoning, studies on the future of cognitive work, and this completely novel benchmark built entirely around a Victorian whodunit board game.
I love this benchmark so much.
Same. We are going to explore how humans and machines solve mysteries differently and why traditional multiple choice tests are fundamentally failing to measure true intelligence. And ultimately, what happens when the algorithms that run our world hit the jagged frontier of their own capabilities. Okay, let's unpack this.
Yeah, let's do it. Because the contrast you've just highlighted, the absolute brilliance right alongside that sudden, almost inexplicable cognitive collapse, that is the defining feature of the tech landscape right now.
Completely.
We've spent decades trying to build systems that think like us, and in the process, we've kind of realized that our methods for measuring thought are, well, they're surprisingly fragile.
Right, the old tests just aren't holding up.
Exactly. The multiple choice paradigms we've relied on for years are breaking down. It's forcing cognitive scientists to return to the drawing board and ask a much deeper question. What does it actually mean to reason through a problem when the rules aren't just neatly laid out for you?
To really grasp the magnitude of that, I think we have to look back at the origins of how we even define problems. One of our core sources on artificial general intelligence pulls from a concept by the cognitive scientist Herbert Simon. This goes all the way back to the 1970s.
Oh, right. The structured versus ill-structured problem.
Yes, he drew this hard line between well-structured and ill-structured problems, and for a long time, the entire field of AI research has been overwhelmingly biased toward the well-structured side.
Which, to be fair, makes perfect sense from an engineering perspective. I mean, a well-structured problem is something like chess or Go or, folding a protein.
Where the rules are absolute.
Exactly. The parameters are fixed, you have a defined problem space, strict legal moves, and most importantly, a mathematically unambiguous goal state. You know definitively when you've hit checkmate.
Right.
The environment is closed, there's perfect information, so nothing is hidden from the players.
But the reality of human existence, right, the type of intelligence we actually need for the real world, that operates almost entirely in the ill-structured domain.
Yeah, real life is messy.
Very messy. Diagnosing a patient in an ER with vague, overlapping symptoms, that's an ill-structured problem. Formulating a corporate strategy in a volatile market, same thing.
Oh, absolutely.
These situations are vexatious, they're shrouded in uncertainty, the rules shift constantly. Honestly, quite often you don't even know what a successful resolution looks like until you're halfway through trying to solve it.
You're just constantly negotiating with ambiguity.
Exactly. But this creates a massive friction point for testing, doesn't it?
It really does. When developers build a new large language model and they want to prove its cognitive capabilities, they can't easily test it on navigating pure ambiguity.
Because it's too subjective.
Right, and they need benchmarks that can be scored quickly, cheaply, and objectively at scale. So historically, that meant relying on data sets made up of multiple choice questions. Data sets like Common Sense QA or Wino Grande. Those have been the gold standard for years.
Wino Grande is particularly interesting to me because of how it tries to isolate common sense. It relies on pronoun resolution tasks.
Oh yeah, give the suitcase example.
Right,
Yeah.
so it'll feed the AI a sentence like, the trophy doesn't fit into the brown suitcase because it is too large. And then it asks the AI whether the word it refers to the trophy or the suitcase.
Sounds simple enough for a human.
Yeah, because to us, the physics of the real world dictate that the trophy must be the thing that's too large. But the AI doesn't have body. It's never packed a suitcase. So if it selects trophy, we kind of just assume it has successfully mapped a conceptual understanding of physical space.
And that assumption is exactly where the flaw is, which is becoming super obvious to researchers now.
How so?
Well, a multiple choice format allows for binary scoring. The answer is either correct or incorrect, but it completely fails to capture the underlying mechanism of thought.
It doesn't show how it got there.
Exactly. It offers no window into open-ended reasoning or synthesis or the ability to justify a conclusion. The answer is literally sitting right there on the page. The AI merely has to calculate the highest statistical probability among the 4 provided options.
So it's basically taking a math test where the teacher doesn't force you to show your work.
Yeah, that's a great way to put it. But the situation is actually much worse than just a flawed testing format. There's this huge structural contamination issue in the AI industry known as data leakage.
Oh, right. Because they train on the whole internet.
Exactly. These models require internet-scale amounts of text. They scrape essentially everything ever published digitally. So if a benchmark test like Wino Grande exists anywhere online, the model has almost certainly processed it during its training phase.
So the implications of that data leakage, they cannot be overstated. It basically transforms a test of reasoning into a test of memory.
It's the equivalent of handing a student the answer key to the final exam on the first day of class.
Wow, yeah. So when a new model gets like a 95% accuracy rate on a benchmark, the public headline reads that the AI mastered human-level common sense.
But in reality, we're often just watching a highly sophisticated retrieval operation. The model is regurgitating statistical patterns it memorized months ago.
We end up falling into a classic logical trap. It's the affirming the consequent fallacy.
Oh, walk me through that one.
So the faulty logic goes like this. If an entity possesses human-like reasoning, it will pass this multiple-choice test. The AI passes the test. Therefore, the AI possesses human-like reasoning.
Ah, right.
We just ignore the fact that there are multiple pathways to arrive at the correct answer, and most of those don't require anything resembling actual cognition.
Right. The distinction researchers make here is insight versus brute force computation. Algorithms are natively built for brute force.
Like trying every number on a lock.
Exactly. If you give a computer a combination lock, it doesn't look at the wear patterns on the metal dial to deduce the code. It just cycles through every possible numerical permutation until it pops open.
But human intelligence is constrained by biological processing speeds. We can't do that.
Right. We rely on insight. That ability to bypass the exhaustive search entirely by recognizing a structural truth about the problem itself.
I love the analogy from the text about this. Imagine you're searching for a diamond in a pitch-black room. Brute force is just groping blindly around every square inch of the floor. Insight is realizing you should just feel the wall for a light switch.
That's a perfect analogy.
But here's my question. If the AI natively can't find the light switch on its own, how do we force it into a scenario where it absolutely has to show its work?
That is the million-dollar question, because that helicopter view, that insight requires a cognitive leap. The AI is stuck on the ground.
Right. And I want you, listening right now, to think about how you solve a problem at your own job. You don't just pick from 4 multiple-choice options. You gather clues, you hit dead ends, you synthesize information over time.
Which is exactly why this whole field of AI evaluation hit a crisis point. If the tests are broken by data leakage and the models can fake reasoning with brute force statistics, we needed a whole new arena.
An arena that mirrors the messy, ill-structured nature of reality.
Yes, where information is incomplete, clues are contradictory, and the picture only resolves over time. And the solution the researchers came up with is genuinely brilliant.
They abandoned digital data sets completely.
Yep. They turned to a physical commercial tabletop board game called Watson and Holmes.
Which is so cool. It's this competitive parlor game where players are Victorian detectives trying to solve mysteries in 19th century London.
And using a physical board game wasn't just like a quirky aesthetic choice. It is a rigorous methodological safeguard.
Because it's not on the internet.
Exactly. Because it's a commercial product, the publishers actively keep the text of the cases offline to protect their IP. The narratives, the clues, the solutions, none of it is in the scraped data sets used to train models like ChatGPT or Claude.
So it guarantees zero data leakage. It's a completely virgin testing ground.
The AI couldn't possibly have memorized the answer key because the answer key only exists printed on a piece of cardboard in a box on a shelf.
It forces the model to encounter the problem fresh, exactly like a human player. But they had to change the rules a bit for the AI, right?
Yeah, they had to strip away the social and strategic mechanics. In the original human version, players use these carriage tokens to bid on visiting different locations around London.
Like trying to lock your opponents out of gathering clues.
Right, but the researchers didn't want to test game theory or resource management. They wanted to isolate pure cognitive reasoning, so they removed all that competitive friction.
So the adaptation turns it into this rigorous, single-player investigative experience, and the architecture operates sequentially. First, the AI gets the case introduction.
Which is about 600 words, usually.
Yeah, it sets the scene, like maybe a wealthy aristocrat was found poisoned in his locked study, and it ends with the core questions. Who is the killer? What's the motive? How is the poison administered?
And from there, the AI gets a list of unvisited locations. The morgue, the suspect's townhouse, Scotland Yard. It has to choose where to investigate.
And when it picks one, it gets the specific text for that location, averaging about 160 words, like a coroner's report or witness statement.
But what's fascinating here is the forced response mechanism. After the initial intro, the AI has to attempt to answer the core questions immediately.
Even before it has all the clues.
Exactly. Then, it visits the first location, reads the text, and has to answer the questions again. It has to update its theories based on the new evidence. After the second location, it answers again.
So it's continuously articulating its evolving understanding of the case. And these are totally unconstrained, open-ended text generations. No multiple choice to fall back on.
It's a fundamental shift from static evaluation to dynamic incremental evidence synthesis, testing what they call naturalistic reasoning.
Which is really just how a mind updates its beliefs when new, sometimes conflicting information arrives.
Yeah, testing its capacity to hold a theory loosely, abandon it when new facts emerge, and forge a new explanatory model on the fly.
It's so much like watching a tightly plotted mystery film. When you watch Knives Out, your brain doesn't just passively record things. 20 minutes in, you're like, oh, the arrogant grandson did it.
Right, you form a hypothesis.
But then an alibi checks out 10 minutes later, and your brain instantly discards that theory and builds a new one around the nurse. You're continuously revising your mental model. The Watson and Holmes benchmark forces the AI to do that exact same cognitive dance.
And the scope of this test is huge. They used 11 distinct cases. On average, each case involves exploring 15 different locations.
It's a lot of reading.
By the end of an investigation, the model has incrementally processed around 2,900 words of complex, interwoven narrative. Across all 11 cases, it has to resolve 37 distinct questions.
Okay, so before we look at how the AI actually performed, because the results are wild, we should establish the cognitive framework here. What specific gears in the brain are actually turning when we, or a machine, try to solve a mystery?
Right, we have to look at the 3 primary modes of reasoning for ill-structured problems. This framework goes back to the American philosopher Charles Sanders Peirce.
He broke human inference down into deduction, induction, and abduction.
Yes. People use them interchangeably all the time, but philosophically, they're entirely different operational modes.
Let's pull them apart. Deduction is the most rigid, right?
Absolutely. Deduction strictly follows established rules. It moves from a general premise to a specific, guaranteed conclusion. If your premises are true, the conclusion logically cannot be false.
It's the engine of formal logic. So in a detective game, deduction is what you use to rule out the impossible. Like, if the victim was poisoned at midnight and suspect A was locked in a jail cell at midnight, deduction guarantees suspect A isn't the poisoner. It's absolute certainty.
Exactly. Now, induction is on the opposite end of the certainty spectrum. Induction is generalizing a broad rule from a limited set of specific observations.
It's probabilistic.
Right. So if you notice a suspect lied about their finances, lied about knowing the victim, and lied about where they were on Tuesday, you inductively reason they're probably lying about Wednesday, too.
It's spotting a pattern. But it never offers absolute certainty, just a high statistical likelihood.
Which leaves abduction, the third, and honestly, the most fascinating pillar.
The classic aha moment.
Yes. Abduction is inferring the best, most elegant explanation for a disparate set of facts. It's not mathematical certainty, and it's not just a repeating pattern. It's a creative, synthesis-driven leap that binds totally unrelated data points into a cohesive narrative.
Wait, hold on. Sherlock Holmes is constantly talking about his deductions. But based on these definitions, isn't he actually using abduction most of the time?
Oh, absolutely. Logicians have been pointing that out for years. Holmes rarely uses pure deduction.
Right, because when he meets Watson, he sees a deep tan, a military bearing, a wounded arm, and just instantly concludes Watson is an army doctor back from Afghanistan.
Which is not a logical certainty at all. Watson could just be a civilian who went on a sunny vacation and fell off a horse.
Exactly. So Holmes takes these disconnected observations and makes a creative, abductive leap to build the most plausible narrative. And that capability is the holy grail for AI right now.
It really is. It maps so closely to psychological frameworks like Daniel Kahneman's dual process theory, System 1 and System 2.
Remind me how that breaks down again.
So System 1 is our fast, instinctive, automatic brain. It's all heuristics and pattern matching. It lets you instantly read the mood of a room or catch a baseball without doing conscious physics calculations.
And System 2 is the slow, deliberate, analytical brain.
Right. It engages when you do complex algebra or carefully plan out a legal argument. And in a real investigation, or in this benchmark, you need a high-speed oscillation between both systems.
You use System 1 to inductively spot something weird in a witness statement, and then System 2 to painstakingly deduce if that anomaly breaks the physical timeline.
Precisely. And to quantify this, the researchers actually built an AI tool to assign an IDA rating to every single question in the game, scoring the required induction, deduction, and abduction from 0 to 4.
And almost none of the questions relied on just one mode, right?
Almost none. They are deeply mixed mode problems. Answering a question about the murder weapon might need an inductive baseline to know if a poison is common, deductive logic to rule out weapons that don't match the wound, and abductive synthesis to explain why the killer chose that specific weapon at that moment.
It's a cognitive decathlon, which makes it a brutally hard test for a neural network.
So with all those rules established, we finally arrive at the showdown: human intellect versus artificial processing.
Let's talk about the human baseline first, because they didn't just use random people from the internet.
No, they meticulously constructed this cohort. They got 5 undergrads from the computer science department at University College London.
The people who are highly trained in logical thinking and algorithms.
Exactly. A huge issue in psychology studies is that online gig workers will just rush through tasks to get paid, which ruins the data. So the researchers paid these students the London living wage by the hour.
Removing any pressure to rush.
Right. And they added a competitive incentive, a double pay bonus for whoever got the highest accuracy score. It created a highly motivated, financially incentivized pool of human intelligence.
And they took it seriously. The median time spent on a single case was 59 minutes.
An entire hour of intense cognitive labor, taking notes, cross-referencing locations, building mental timelines.
It's a rock-solid, expert-level human baseline. Facing off against them were 2 generations of AI, which the researchers call CModels and R models.
The architectural difference between those two is the key to this whole study.
Okay, break that down for us.
So COFLs are completion models. This is the paradigm that ran the industry up until very recently. Early ChatGPT, early Claude, they operate fundamentally as autoregressive text predictors.
Which means they are essentially highly sophisticated autocomplete engines.
Exactly. You feed it a prompt, and it calculates the mathematical probability of the next word, outputs it, recalculates, and outputs the next, token by token.
It doesn't pause to think, it just starts talking.
Right, it doesn't reflect. But the R models, the reasoning models, are a structural paradigm shift. Systems like DeepSeek R1 or OpenAI's O3, they use heavily scaled reinforcement learning for what's called test-time compute.
This is the really cool part. When an R model gets a prompt, it doesn't immediately output an answer. It uses compute resources to generate a hidden chain of thought internally.
It builds a private sandbox. It talks to itself before it speaks to us.
Inside that hidden chain, it proposes a hypothesis, runs a simulated check against the evidence, realizes it's wrong, backtracks, and tries a new logical path.
It mimics that slow, deliberate System 2 analytical processing, like a human doing math on scratch paper. Only after it resolves the internal logic does it output the final answer.
Now, to grade all of this, thousands of paragraph-length responses across 11 cases. They used a 0 to 3 scale. 0 is totally wrong. 3 is perfect comprehension.
But grading all that text manually would be a nightmare. So they engineered an AI autograder using GPT 4.1.
Which instantly sounds sketchy. Using AI to grade AI.
I know, the immediate reaction is deep skepticism. But they anticipated that. They had human experts manually grade a massive subset of responses to cross-reference.
Lan.
The AI autograder matched the human experts 85 to 88% of the time.
Which is statistically super robust. That's about the same agreement rate you'd get if you gave the same college essays to 2 different human professors.
Exactly. The grading mechanism was totally sound.
Okay, here's where it gets really interesting. The data on the progression of AI capability over a condensed 9-month window in 2025.
The velocity is just staggering. It defies historical tech curves completely.
At the start of those 9 months, the models entering the benchmark performed roughly at the lower quartile of the human students, like that distracted undergrad struggling to connect the dots.
But by the end of those 9 months, the newest generation of our models violently detached from the bottom of the graph and surged into the top 5% of human capability.
They became master detectives almost overnight. The highest performing R model, O3 Pro, definitively crushed the absolute best human player in that highly motivated UCL cohort.
The machine won the decathlon. It completely validates the shift toward test time compute. When an AI is given the architectural space to build an internal chain of thought, its abductive reasoning scales exponentially.
And we also have to look at the economics here. The study maps this out using a log 10 cost trend. It's not just that they're getting smarter. The computational cost to generate that high-level reasoning is plummeting logarithmically.
The newer, smarter models are hitting expert scores while consuming a fraction of the compute power and money that the older, less capable models needed.
We're entering an era where profound cognitive processing is becoming a cheap, abundant commodity.
Right. And if we stop the analysis right here, the story is pretty straightforward. AI has conquered ill-structured reasoning, and human cognition is devalued.
Yeah.
But the true value of the Watson and Holmes benchmark is that it reveals the profound, almost alien structural vulnerabilities that still exist in these systems.
When we dig into the specific location-by-location data, the frontier of AI capability isn't a smooth curve. It's incredibly irregular.
Which brings us to the jagged technological frontier.
Right. This is a framework from a landmark study by the OECD and the Boston Consulting Group. They took 758 elite management consultants and gave them AI tools for their daily workflows.
And their findings perfectly illustrate this jagged landscape. For tasks inside the AI's zone of competence, even really complex analytical tasks, the consultants using AI were 25% faster and their work was 40% higher quality than the control group.
A massive force multiplier.
The crucial discovery was what happened when tasks shifted just slightly outside that invisible frontier.
Problems that looked exactly as difficult to a human.
Yes. For those tasks, the consultants relying on the AI were actually 19% less likely to get the correct solution than those who used no AI at all.
Because the AI confidently hallucinates basic logic if the parameters shift even slightly. The frontier is literally a jagged cliff.
And humans naturally develop strategies for this. The BCG study categorized workers as centaurs or cyborgs.
Centaurs delegate at a macro level. They give the highly structured analytical stuff to the AI and keep the ambiguous empathetic tasks for themselves.
While cyborgs do micro-level integration, they continuously weave their own cognition with the AI's output, checking and guiding it step by step to keep it from falling off the cliff.
Applying that lens to the detective benchmark, those jagged cliffs become glaringly obvious. The AI operates with terrifying brilliance in some areas and suffers total cognitive collapse in others.
The brilliance is mostly in inductive reasoning during the earliest stages of the game.
Right after reading the 600-word intro, when evidence is super sparse, the human players score low here, they're cautious, they know they don't have enough data yet, so they hedge their bets.
But the reasoning models, they make highly accurate inductive leaps based on microscopic hints.
Like noticing a tiny mention of the chemical makeup of mud on a shoe, cross-referencing that against its vast knowledge of 19th century London industrial zones, and correctly guessing the killer's profession before visiting a single location.
It's breathtaking pattern recognition. No human could match that encyclopedic recall.
Yet the benchmark also exposes a catastrophic vulnerability related to the physical length of the narrative. As the word count pushed past 1,900 words into the 3,000 to 4,000 word range, both CODLs and R models completely degraded.
Total collapse.
Hold on, this is the part that drives me crazy. Every tech company advertises massive context windows. They say these models can hold millions of tokens. They can read War and Peace in seconds. Why are they tripping up over a 3,000-word mystery? That's the length of one chapter in a novel.
If we connect this to the bigger picture, it comes down to the mechanical difference between data retrieval and multi-hop reasoning.
Okay, unpack that.
Massive context windows are great for retrieval. If you put a 500-page legal doc into a million-token window and ask it to find a specific clause on page 200, it will retrieve it flawlessly. It's just a sophisticated search query.
But Watson and Holmes isn't a search query. It's multi-hop reasoning. You extract a subtle clue at location 1, hold it in active evaluation, find contradictory evidence at location 5, synthesize them, abandon your first theory, and carry the new idea to location 10.
And this is where the underlying math, specifically the attention mechanism of large language models, starts to work against it.
Right.
The attention mechanism calculates the mathematical relationship or the weight of every single word against every other word in the sequence.
It creates this enormous matrix, which works fine in a short text. It perfectly understands that it refers to the suitcase.
But that matrix scales quadratically. When the word count doubles, the mathematical connections don't just double, they square.
So a 3,000-word text generates millions of intersecting attention weights.
And the result is an overwhelming accumulation of mathematical noise. The attention gets diluted across thousands of irrelevant tokens. It remembers the color of the curtains, the weather outside, the brand of tea, and it assigns mathematical weight to all of it.
So the signal-to-noise ratio just collapses. The crucial multi-hop connection about the poison gets totally drowned out by narrative text.
Exactly. Contrast that with human working memory. We're terrible at storing verbatim text. If I asked you to recite a chapter you just read, you'd fail.
Oh, totally.
But we have profound biological efficiency. We use symbolic compression. We build abstract mental models.
When we read a mystery, we naturally filter out the noise. We discard the curtains and the weather. We grab the red threads, the motive, the timeline, the weapon, and build a simplified, cohesive model of the crime.
And when a new clue pops up 10 pages later, we don't scan backwards through every word. We just plug the new concept into our mental model to see if it holds up.
Artificial neural networks don't natively do that. They don't build abstract, filtered mental models. They're forced to calculate the entire matrix constantly. They lose the plot because they literally can't separate the signal from the noise over a long sequence.
It's a very human way to fail, getting distracted and losing the thread, but it happens for entirely non-human algorithmic reasons.
It really highlights that while our models simulate high-level abductive reasoning, the architecture is still fundamentally alien to biological thought.
The machine can outdeduce and outinduce us in short bursts, but it completely lacks the narrative endurance of human symbolic modeling.
So taking a step back, this deep dive paints a really complex picture of our tech trajectory. We started by realizing that multiple-choice tests are structurally compromised by data leakage. They fail to separate brute force from genuine insight.
And shifting to this analog, ill-structured, zero-leakage board game gives us a much clearer lens.
We see reasoning models evolving at a staggering pace, mastering detective leaps in months. But their reliance on quadratic attention makes them highly vulnerable to narrative noise. They conquer the jagged frontier, only to fall off a cliff when the story gets too long.
And the implications extend way beyond a tabletop game. It reshapes our understanding of the future of labor. We also looked at a comprehensive study by the Allied Business Academies on skill requirements in the age of generative AI.
That study projects a massive realignment. As AI colonizes the well-structured parts of the economy, automating data processing, standard coding, routine corporate analysis, the premium on specific technical skills is projected to shift by 40%.
The economic value of the human worker is migrating rapidly toward the exact cognitive functions where AI still stumbles.
Complex, ill-structured problem-solving, navigating deep ambiguity.
Yes, the creative capacity to build coherent mental models out of chaotic environments. The human mind is still the ultimate engine for mapping the unknown. The AI is a phenomenally powerful engine inside a structured space, but a human has to define the structure of the space itself.
We are the centaurs and cyborgs managing the frontier. And that dynamic leads to a final, slightly provocative concept that I really want you, the listener, to carry with you today. The researchers analyzing the benchmark coined a term that perfectly encapsulates this era: anthropogenic debt.
Anthropogenic debt. It's the invisible reliance that artificial systems have on human creation.
Think about the architecture of this benchmark we just spent an hour dissecting. The O3 Pro reasoning model achieved a master detective score. It outplayed the humans at the game. But
a human game designer had to painstakingly invent the rules of that game.
exactly. A human author had to sit down and write the 600-word introduction. A human intellect creatively devised the murder method, hid the clues, and structured the underlying logic of the Victorian world the AI was navigating.
The AI is a master puzzle solver, but it remains completely dependent on a human to construct the puzzle box.
It lacks the generative insight to build a cohesive, ill-structured mystery from scratch. The machine can perfectly execute the role of Sherlock Holmes, but it cannot play Arthur Conan Doyle.
It's a profound limitation.
So as these models grow exponentially more powerful, and as they voraciously consume every piece of human-generated data on the internet, we're approaching a really fascinating horizon line. What happens when we run out of anthropogenic debt?
What happens when the AI solves every puzzle we've ever written?
Exactly. What happens when the master detective is finally forced to start inventing its own clues? It's a question that pushes us past the jagged frontier and into entirely uncharted territory. We are going to leave you to ponder the architecture of that future puzzle box. Thank you so much for joining us at the table today for this deep dive. Keep questioning the structure of the information around you, keep relying on your own mental models, and we will see you next time.